fluorenone. Fluorenone is a molecule made of these pieces: 13 carbon atoms, 8 hydrogen atoms, and 1 oxygen atom, put together like this. A more streamlined way of depicting the molecule is with a skeletal structure, which looks like this. In a skeletal structure, the kink at the end of each line represents a carbon atom, and the hydrogen atoms coming off of those are implied. Fluorenone in nature. While fluorenone itself is not the most common molecule in nature, there are derivatives of fluorenone, molecules that are similar to and made from fluorenone, that do occur. A really common derivative occurs in many plants and is used as an antimicrobial agent to kill common microbes that might infect the plant. Microbes that also infect humans, like here you have Candida albicans, Escherichia coli, and Saccharomyces cerevisiae. And these fluorenone derivatives will harm and kill these microbes and prevent them growing and attacking the plant. How humans use fluorenone is similar, and it's also with fluorenone derivatives, so not fluorenone itself. When a mosquito bites you, its saliva drips into your blood, and that saliva can carry a lot of smaller microbes and bugs. One of those microbes is a Plasmodium microbe. That doesn't occur in all mosquitoes, but if it does occur in a mosquito, when the mosquito bites you and the saliva drips into your bloodstream, that Plasmodium microbe can inject itself into your red blood cell. That's what's happening in this image here. And that will cause malaria. Malaria is a disease that has a lot of flu-like symptoms. You'll have headache, fever, shivering, joint pain, vomiting, convulsions in the worst cases. And there are derivatives of fluorenones that are used to treat malaria, this Plasmodium disease that's propagated through mosquito bites. Fluorenone itself, not a derivative of fluorenone, but fluorenone itself is used sometimes to add odors or smell scents to candles. And derivatives of fluorenone are sometimes used to counterbalance androgens. Androgens are hormones that develop male gender characteristics. So the depth of your voice, the amount of hair on your face or body, those are caused by hormones called androgens. And both men and women have androgens in different amounts. There are some women who have high levels of androgens, and that can cause certain conditions that, like what is in front of you here. This is, you can see there's a large amount of hair growing on this woman's chest. And so you can treat that large amount of androgens with derivatives of fluorenones. Safety with fluorenone. When you're thinking about trying to summarize the safety of a molecule, it's convenient to look at these safety squares or fire diamonds. The blue fire diamond on the left represents the hazard a molecule might represent to your health. It's on a scale from 0 to 4, where 0 represents no health hazard, and 4 represents a quick death on exposure. Fluorenone is a 1 on that scale. If it comes into contact with your skin, it'll cause skin irritation, and you want to prevent that by wearing gloves when you work with fluorenone. If it comes into contact with your eyes, it will cause eye irritation. You want to prevent that by wearing goggles when you're working with fluorenone. And if you breathe in fluorenone dust or vapors, it will cause respiratory tract irritation. So you want to make sure when you work with fluorenone, you work with it in a well-ventilated area, preferably a fume hood. Chronic exposure, so repeated exposure over a long period of time in animals, there have been reports of development of tumors in those animals after that chronic exposure. Not acute exposure, one time for just a short period of time, but repeated exposure over a long period of time. So there's a possibility that at higher concentrations with repeated exposures, fluorenone is carcinogenic. The red box at the top of this fire diamond represents flammability. It's also on a scale from 0 to 4. In this case, 0 means the molecule will not burn, and 4 means that it's a flammable gas at room temperature that could be ignited even just by friction in the room. Fluorenone is a 1, And what that means is you don't want to expose it to excessive heat, to spark, or to flames, because it could burn. It's not going to burn at low levels of heat, but it could burn if you expose it to spark or flames. And the fumes of fluorinone are toxic. So it's a 1 on this fire diamond. The yellow square at the right represents instability or reactivity. This is basically explosiveness. And it's also on a scale from 0 to 4. In this case, 0 means the molecule will not explode no matter how much you shake it, and 4 means it will explode at room temperature if you disturb it. As a 0, you don't have to worry about fluorinone exploding in your hands in the lab. Because the white diamond at the bottom is blank, there are no special considerations you have to take into account when you're handling fluorinone. Visualizing fluorinone. As we saw, fluorinone can be depicted as in a skeletal structure like this, where each of the carbons and hydrogens are represented like so. Now this is a 2-dimensional representation of a 3-dimensional molecule. In 3 dimensions, fluorinone looks like this. Notice that each of the carbons in fluorinone is trigonal planar. Those gray balls there are trigonal planar. Those are the carbon atoms. In this image, you'll notice there are also colors here. The colors, a colored image like this is called an electrostatic potential map. In the electrostatic potential map for fluorinone, the red represents places where electrons tend to accumulate. You'll notice oxygen is electronegative, so it tends to pull electrons to itself, and it becomes slightly negative. And that's represented by this red color here. Blue is a place where you are missing electron density. Electrons have migrated away from there, and so they've taken their charge with them, and those places tend to be slightly positive. That's what's represented by the blue color. On the whole, the molecule tends to be more greenish. The green in this image, this electrostatic potential map, represents places in the molecule that are neutral, that have neither partial positive nor partial negative charges. The bonds in fluorinone are not static and still. They vibrate and twist and turn. In fact, in 1 second at room temperature, the bonds in fluorinone will vibrate around 10 trillion times. To help you to visualize, give you a visual sense of what those molecules look like when the molecule is living and breathing and moving around and dancing in a beaker, consider this simulation here. I've played this simulation at a speed where you can sort of track and follow the vibrations and movements of the atoms. But we live over enormous timescales compared to atoms. In 1 second, an average bond will vibrate around 10 trillion times. Now we can't imagine, we can't visualize a vibration happening 10 trillion times in 1 second. We experience things in seconds. So to help you visualize, maybe get a little closer to what the molecule looks like in reality at room temperature, let's speed this up. This is the molecule vibrating 20 times faster than the original simulation. Let's speed it up even more. This is the molecule vibrating 400 times faster than the original simulation. In reality, you would have to speed this up 25 billion more times before you get to the amount of movement that's happening in each fluorinone molecule in a grain of fluorinone at room temperature. Now, we're not only enormous in terms of time, we don't only exist over eons and epochs, we also are enormous in terms of size. Every time you exhale, you breathe out more atoms than there are stars in our galaxy. And when you zoom out, and you have a collection of hundreds of trillions of fluorinone molecules, you zoom out, the molecules are so small that we can't distinguish them individually. Rather, they merge together like pixels on a screen, and they create the experience in our brain of a light yellow solid. And you can see that solid here. 1 grain of this solid contains about a quintillion fluorinone molecules. A quintillion is 1,000,000 trillions. That's in 1 of those grains of fluorinone. Physical properties of fluorinone. Physical properties are the properties that you get when these molecules accumulate into huge populations. Physical properties are the personality traits of those huge populations. of those molecules all acting together. You can look up the physical properties of fluorenone and other molecules in reliable handbooks like the CRC handbook that you see on the left here, or the Merck index that you see on the right. One physical property has to do with the phase of the substance. Is fluorenone a solid, a liquid, or a gas? Well, that depends on what temperature fluorenone is at. Fluorenone will either be a solid or a liquid or a gas, depending on the temperature. At temperatures below 183.2 degrees Fahrenheit, fluorenone will be a solid. Between 183.2 and 646.7 degrees Fahrenheit, it will be a liquid. And above 646.7 degrees Fahrenheit, fluorenone will turn into a gas. Now let's try to intuitively understand these numbers. Water freezes at 32 degrees Fahrenheit and boils at 212. So fluorenone tends to be mostly a solid in those temperature ranges, although as water gets close to boiling, fluorenone might turn into a liquid. Another way to sort of intuitively understand these higher numbers is your oven. When you bake something like vegetables or frozen pizza, you heat your oven up to maybe 400, 450 degrees Fahrenheit. At that temperature, fluorenone would still be a liquid. It wouldn't be until you get it to around 646 that it starts turning into a gas. As a scientist, you want to be able to think not just in degrees Fahrenheit, but also in degrees Celsius, especially in degrees Celsius. And so fluorenone will be a solid below 84 degrees Celsius. It will be a liquid between 84 degrees Celsius and 341.5 degrees Celsius. And it will be a gas at temperatures higher than 341.5 degrees Celsius. Compare that with water. Water is a solid below 0 degrees Celsius and boils it turns into a gas at 100 degrees Celsius. These temperatures where the molecule freezes or boils, these freezing points or boiling points, can also be used to separate and purify molecules. For example, if you had a mixture of fluorenone with other things, you could maybe, for example, cool it. If it was a very hot mixture, you could cool it down to 84 degrees Celsius so that fluorenone would solidify out and the other molecules would stay liquids. And then you could separate that. When you separate molecules based on their freezing points, it's called crystallization. On the other hand, you could, if you had fluorenone in a mixture, you could heat it up until it was 341.5 degrees Celsius. The fluorenone would boil away as a gas, and the other molecules may stay in the liquid. And so you can collect that gas vapor, for example, like vapors collect on the bottom of the lid of a pot if you're boiling spaghetti, and collect that, have it drain into another container, and you could separate the purified fluorenone in that way. When you separate molecules, purify molecules based on their boiling points, that's called distillation. So these physical properties help you to separate and purify things. Another important physical property is solubility. Solubility is significant because it creates structure within a fluid. You can imagine how important that is for living things, which are essentially made of structures in fluids. Let's think about the solubility of fluorenone in water at room temperature. Solubility, whether molecules mix or not, really depends on the charges that are spread out in the molecule. Water is a molecule that has charges on every single atom. The oxygen is very electronegative, so it pulls electrons to itself, becomes slightly negative. You can see that in the red of the electrostatic potential map. Those electrons move away from the hydrogen, so they're slightly positive. Now, one water molecule is going to want to stick to other water molecules because opposite charges attract, and a negative oxygen will be attracted to a positive hydrogen of another water molecule. A different molecule will only mix with water if it also has negative and positive charges that can compete with the negative and positive charges of water molecules, so that water will want to stick with it and surround it. Then it would mix with water. In fluorenone, although the oxygen does have a slight negative charge, and although these hydrogens may have a slight positive charge, on the whole the molecule is so big that these slight charges on individual atoms are not big enough to compete with other water molecules. Rather, water will stick to itself and exclude fluorenone. So fluorinone is insoluble in water at room temperature. It does not dissolve in water at room temperature. Another important physical property, a last one, is density. Density is significant because it creates structure based on sinking and floating. More dense objects sink, less dense objects float, and that creates layers. Layers like the core, mantle, and crust of the Earth, or layers like the hard parts where the oil in peanut butter that's been sitting for a long time. So the density of fluorinone is 1.13 grams per milliliter. Compare that with the density of water. The density of water is 1 gram per milliliter. Because fluorinone has a higher density, it will sink when you put it in water. Hopefully this video has given you some insight into the molecule fluorinone.